is a little bit of a concept of like what's this deal with asymptotes. So let's suppose that we just had, and I just want you to watch at this point, but let's suppose we had some sort of function that, I don't know, maybe did something like this. If we all of a sudden stuck a restricted domain value into this function, if we kind of created, an x value that was not okay, basically, that's what creates those vertical asymptotes. And what's interesting is if all the rest of the equation that produced that green curve still existed, but then there was this extra thing that created the asymptote, the curve doesn't come right up to the asymptote at that point, like a piecewise function would. Instead, the curve tries to adjust around the asymptote. It tries to continue to go. So in this case, maybe this would end up going like that, and maybe this one would end up going like that. And so it's because there's a physical equation involved. It's like the math doesn't just stop. Right? The math doesn't just stop because there's one x value that doesn't work. You can continually plug in x values, getting closer and closer to that asymptote, and then have that equation spit out y values for you. And so your function continues forever as you get closer and closer to that asymptote. And so that's called asymptotic behavior. It's also called end behavior. When we saw growth and decay functions, if we saw like a growth function here, this end going left was guided by the asymptote, all right? It did not randomly just start pointing away from the asymptote. So sometimes we think of those asymptotes as like magnets. They are pulling that function towards it. Now, for right now, asymptotes are lines that we do not ever touch and we do not ever cross. However, that will change before the end of the week, okay? But in general, we do not ever cross or touch asymptotes. Alrighty. So you can kind of see, I just sort of summarized that warm-up concept right here. When we graph exponential and logarithmic functions, what do we include on the graph because it models the end behavior of the function? It's an asymptote, right? An asymptote is what guides that end behavior. All right, so what I want to do here is I want to jump right into how would you graph one of these, okay? So let's do this together, and hopefully it will kind of recap some of these things from last Thursday. These are a set of questions that will be repeated over and over. Every graph will have this set of questions, possibly some other questions off to the side. You will see these abbreviations. So let's go first with the vertical asymptote. So a vertical asymptote, that is a restricted x value. Does anybody remember where it comes from in the equation? Gavin?
Is it if there's like a number after the fraction?
Oh, you're close. If there is a number after, that is your horizontal asymptote because that's an up-down movement. The vertical asymptote comes from the zeros of the denominator, the zero makers. So the zero maker of the denominator. And so the zero maker of the denominator in this case would just be 0. So my vertical asymptote is at x equals 0. So I'm going to draw that in. When it's on the axis, just do a dashed line like right next to it, or maybe use a highlighter. That could help as well. Our horizontal asymptote, since there was no k value added at the end, it is just a 0, and so therefore we have a horizontal asymptote at y equals 0. All right, now the word roots. The word roots is a fancy word for x-intercepts. Okay, if you don't remember that, we saw that a lot in chapter 6. So an x-intercept means I need to find the x value when the y value is 0. So I'm going to plug in a 0 for y. I will get 0 equals -3 over x. Maybe I just slap that over one, do my cross products. -3 is equal to 0. Is -3 equal to 0?
No.
And it will never be equal to 0, right? So this means there are none. So if you find yourself in a weird situation like that, you may not have done anything wrong. Now, does that make sense that there would be no x-intercepts? Yeah, there's an asymptote there. Okay, so those two things often go hand in hand. What about y-intercepts? So y-intercepts, plug in a 0 for x, find y. And in this case, I would get -3 divided by 0. Oh, can I divide by 0? No, I really shouldn't. So that is also none. All right, so that combination of things often happens when your asymptotes are on the axes. So I did want you to just see what that's going to look like. It looks a little weird. So now what we have to do is we actually have to graph, we have to figure out what our function looks like, but we don't have any points. And so when you are in this situation, you literally are just going to make a t-table and plug in a couple points. You don't have to do that many. So let's start off. On the right side and just pick an x value somewhere on the right side. How about a 1? And we're just going to plug it in, and we would get -3 over 1, which is -3. So I know for a fact this function goes through the point 1, -3. Now the nice thing about these graphs is we are only expecting you to do rough sketches. So honestly, this 1 point is probably enough for you to know that you've got a curve that's going down and following that asymptote, but also coming up and following this asymptote. Yeah?
So we have to indicate a point because then you could just draw it. Okay.
You do need to indicate a point. Not always. You'll see as we move on. Sometimes you don't. But for this kind, you do. You know, if you wanted to do more than 1 point, what if I plugged in a 3? Let's see here. I would get -3 over 3, so I would get -1. And look at that. That's right about where my curve is anyway. So now, I know I have another curve. Now, process of elimination. It's definitely not in quadrant 1, because then it would fail the vertical line test. Okay. It could definitely be in quadrant 2. And it's actually possible that it could be in quadrant 3. We haven't seen that yet. We will see that this week. So it's somewhere over here. Plug in a point to figure out where. So how about plug in -1? Plug in -1, you're going to get -3 over -1, so therefore you get a 3. So over -1 and up 3. And here's my curve. Sometimes they will have these sort of symmetric points, but not all the time. So I usually just do a t-table for that. Domain. The domain is, notice it goes left forever and it goes right forever, but there's one place where it breaks. It breaks at that vertical asymptote. So the domain goes from -infinity up to 0, and then it stops. And then it jumps over on the other side from 0 to infinity. Yeah, Alex.
How many points do we need on, I guess, each curve?
Good question. In some cases, 1 will be enough. So for these curves, just 1 kind of indicating to you, oh, it's definitely up here and not down there is enough. As we move through the week, I'll indicate to you when you would need more than 1 point. All right, any basic questions about that before we move on? Okay. I think, you know, these are pretty straightforward. The steps you follow are always the same. So let's try this one. We've got, in this case, let's do our vertical asymptote first. So 0 makers of the denominator. So in this case, my vertical asymptote would be at x equals 1. Awesome. So we'll draw that in. And our horizontal asymptote would come from any number hanging out at the end, which you can see right here is -2. So that would be at y equals -2. This is going to be your favorite kind of graph because this is actually going to be quicker and easier. I don't think I'm going to need any points to figure this one out. I do need to kind of finish answering these questions though. Let's do our roots, which are x-intercepts. So I'm going to plug in a 0 for y. So I will get 0 equals -3 over x minus 1 minus a 2. This does occasionally require just a little bit of math. Add the 2 over. 2 is equal to -3 over x minus 1. Then do your cross products. 3 equals 2x minus 2.
Would it be -3?
Yeah, I'm like, wait, what's happening here? Yeah, -3. Add that over, I get -1 is equal to 2x. Let's see. All right, so x is -1/2 when the y value is 0. All right, so x is -1/2 and the y value is 0. So right here. All right, let's try our y-intercepts. In this case, the y-intercepts, I just plug in a 0 for the x value. This one's always easier. Y equals -3 divided by -1 minus a 2. So that's 3 minus a 2. So that's a 1. So that's right here. All right, now, so that we can have the same language, when the asymptotes move off of the axes, I still want to be able to talk about sort of the 4 areas that they create. So I'm going to call them zones instead of quadrants, because that way we can still maintain quadrant 1, quadrant 2, 3, and 4. I'm going to call this zone 1, this over here zone 2, zone 3, and zone 4. So we definitely have a curve in zone 2. With 100% confidence, I know we do because we have points there. So my curve needs to go through those points. It will then approach the asymptote. Over time, it will also approach this asymptote over time. So it will ride that space in between the axis and the asymptote. Now, what I'd love to be able to do is get you to the point where you can use your intuition about functions to figure out where the next piece is without doing too much work. I can tell you right now, we can definitely rule out zone 3, because then it would fail the vertical line test. So we definitely know it's not there. So then the question is it in zone 1 or is it in zone 4? What do you think, Abby?
Zone 4.
It is in zone 4. Now, the question is, are you doing that because you tend to see them on diagonals, which is good. We will see them side by side. The other thing is, what about this right here? That's an axis. If I had a curve that was going to be right here, it would need to cross that axis at some point to get to the asymptote. We don't have a point.
There's 2 lines.
Yeah, we already plotted our only x-intercept. We don't have a point over here. So I know for a fact there's no way my curve could be there. Therefore, with confidence, I can draw a rough sketch of the other curve right here. So in this particular problem, I would not expect to see a t-table. If I saw a t-table, that'd be totally fine. But I would not necessarily expect it because I think that you could come to a conclusion that that's where the curve was without a t-table. Domain, -infinity up to what?
1.
Up to the 1, and then 1 to infinity. All right, so take a look at this equation, which is the one we just graphed. All right, this is kind of like a subtraction problem in weighting, right? You got a fraction minus a whole number. I want you to take a minute and perform that subtraction. So there's space right here. I'll help you get started. You're gonna need a common denominator. That common denominator would be x minus 1. So do that right now.
It's gonna equal y.
Yeah, don't even worry about the y or the equals. Just perform this subtraction. Careful with this right here. All right, so I believe you should have gotten. Thank you. believe that's what you should have gotten. Yes.
So we're just supposed to just ignore the y equals until the end?
Yeah, really, I'm just simplifying the right-hand side. Okay, now, the reason I wanted to have you go through this activity, do you agree with me that doing what we just did didn't change the function?
Yeah.
Wait, I'm confused. I thought if we did the lowest common denominator or whatever, we had to multiply both numerators by the same thing. So if we multiply -3
But this already has the denominator.
So when that cancel out?
But it doesn't get multiplied by anything because it doesn't need its denominator to change.
Oh, okay.
Right? This one kind of has to match it. So what I want you to think about here is I just performed a subtraction problem. I made it look different. This is the exact same equation as this. This would have a graph that's exactly the same as this. And the big takeaway from today is that it's not always going to come to you looking like this. This is nice. When it comes to you looking like this, you can tell right away where that horizontal asymptote is. Oh, it went down to. Boop, 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 easy. But it's not always going to come to you looking like that. Maybe it comes to you looking like this. And how would you know where the horizontal asymptote is if there isn't a number hanging out at the outside? So that's today's big lesson. What do you see that's different with this version of this equation compared to this one? What do you see? You have your roots and your y. I think there are roots and y-intercepts kind of showing pretty easily. What else?
There's x's in the numerator and the denominator.
Look, all of a sudden there's an x in the top. This did not have an x in the top. That's what I want you to pay attention to, because here's the rule. All right, so the rule is, when it looks like an x on both the top and the bottom, sometimes we call that same over same, because this is x to the power of 1 over x to the power of 1. So when we have same over same, your horizontal asymptote is going to be the coefficients of the x in a ratio. So the horizontal asymptote is at y equals the ratio of the coefficients of x. I'll put it side by side with its graph. Wasn't its horizontal asymptote at -2? And here, when we performed that subtraction, we got the coefficients -2 over 1. So that's what you have to be prepared for. It won't always have a plus k, plus or minus k. So you have to look out for what if it's got an x on the top and on the bottom. In that case, you take the coefficients. Yeah.
So like if it was -2 and -2, then the ratio would just be 1.
Yes, exactly. So then you would do the reducing of those. Good. All right, let's try one of those. Let's graph one of those. All right, so when you kind of go through this set of questioning, when you go to figure out the horizontal asymptote, you could look at this and go, ooh, this is same over same. That's a common language. You'll hear like other students, other teachers using that language. So in that case, we're going to grab the -2 and we're going to grab the 1. And so my horizontal asymptote is y equals -2 divided by 1, which is just -2. And I can plot that. All right, my rule about my vertical asymptote hasn't changed. It's still the 0 maker of the denominator. So in this case, it would be x equals -3. All right, let's do our x-intercepts and y-intercepts, because sometimes those are the only points we need to do. So plug in a 0 for y. I'm going to get 0 equals -2x over x plus 3. Swap that over 1. Do your cross products. -2x equals 0. So x equals 0. All right. So I've got a root at 0, 0. Now 0, 0 is kind of a special point. What's What's my y-intercept going to be? Also 0, 0. Guess what? The origin is the only point that's both x and y-intercept. All right. So let's see if we can figure out our curve here. I am positive that I'm going to have a curve that goes through those points. And I think I can guesstimate that it's going to go like that, and then it's going to approach this asymptote, and that's good. I don't think I need another point to clear that up for me. So the question is, do I know where the other curve is without plugging in a point? How about show of hands, zone 2, zone 3, or zone 4? Where do you think it's going to be? Your intuition is strong, my friends. It is in zone 3. All right. Can somebody explain why not zone 2? Okay.
We have to have an x-intercept, and the one that's in zone 1 already has an x-intercept.
Exactly. Look at that axis right there in zone 2. So that's going to help you rule that out. Awesome. Okay. So there you go. All right, so let's see about this one. Okay, vertical asymptotes, 0 makers of the denominator. So what, a 3? All right, horizontal asymptote. Is this same over same?
No.
No, so then this is a plus 0 at the end. That's how I know it is y equals 0. So in this case, it's not same over same. All right, roots, got to calculate those. Plug in a 0 for y, so 0 is equal to 4 over 2x minus 6. Use your cross products, and you're going to get 4 equals 0.
No.
Now. Oh, I might have caught that faster if I had graphed my horizontal asymptote. Now I can see why I don't have any x-intercepts, because there's an asymptote there. All right, now what about y-intercepts? Plug in a 0 for x. Now, in this case, I would get y equals 4 over 0 minus 6. Ooh, so negative 2/3. You could have none on one of them, but still have a value on the other one. So over 0 down 2/3. So you can guesstimate that. And the reason I say you can guesstimate its location on the graph is because you're going to have it written over here. There's going to be a blank that you're going to fill for that. All right, I believe we can go ahead and draw our curve here, going through that point. And then the question is, do we know where the other one would be? I think it's either in zone 1 or zone 4. In this particular problem, you would not want to just guess. In this particular problem, you would want to back yourself up with like 1 point. Do 1 point in a t-table. What would be an x value that I could choose?
4.
Yeah, how about 4? Make it easy. Just make sure it's over here. So if I plug in a 4, I'm going to have 4 over 8 minus 6. So 4 over 2, so 2. So I have the ordered pair 4, 2. Great, and that's enough. When I'm grading something like this, I would have like some points assigned to, did you do a t-table to figure out whether it was up here or down here? And did you plug it in correctly and plot it correctly? Domain, in this case, is negative infinity up to the 3, and then stop 3 to infinity. Some of you like rules, right? Like, just give me a rule that I know I can follow. It would be okay, sort of, for you to think of it like this. But I don't like blanket rules because before the end of the week, there's going to be some add-ons to that rule. There's going to be other things that break the domain besides vertical asymptotes. All right, so what about this one? Is this one same over same?
Yes.
Aha, all right. So for this one, I do have same over same. So when I see that, I'm going to go, okay, my horizontal asymptote is at y equals 3 over 1, so it's at y equals 3. My vertical asymptote would be at x equals -2. My roots, let's see, 0 is equal to 3x minus 1 over x plus 2. Hey, Nate, you mentioned that like when it was in same over same, it was really easy to see those. So where does the x-intercept come from? You're close. It comes from the top. This is where the vertical asymptote comes from. The zero maker of this is the x-intercept. Because when you cross multiply, you're going to get 0 equals 3x minus 1. So the zero maker is what, 1/3? So sometimes that's a shortcut for finding your x-intercepts. It's what makes the top 0. So over 1/3 of 0. Y-intercept, plug in a 0 for x, try to find y. I'm going to end up with what, -1/2? Because it's 0 minus 1 over 0 plus 2. Over 0 down 1/2, so like here. And I think I've got everything I need. Gonna have a curve going through these points towards the asymptote, back towards the asymptote. And then what do you think? Zone 1, 2, or 3? Definitely 2. And I don't think you need to show me an ordered pair to know that. So this is the set of questions that you'll get asked. Once you fill that out, you'll see it's pretty straightforward. Sometimes you might have to do 1 or 2 other points at most. Be sure your asymptotes are clearly graphed and the roots and intercepts can be seen. Those will be helpful.